What if I give Aspen HYSYS nothing but pure carbon and hydrogen? Could it predict the formation of methane? Would heavier hydrocarbons such as ethane, propane, or even butenes appear? And most importantly, which products would be thermodynamically favored? In this video, we will use a Gibbs reactor in Aspen HYSYS to let thermodynamics decide the final equilibrium composition. Let's find out what happens. Hello everyone, welcome back to Chemical Engineering and Aspen channel. I am Dr. Mohammad Haris Humayun, and in today's tutorial, we will investigate the production of hydrocarbons from elemental carbon and hydrogen using Aspen HYSYS and using the Gibbs reactor model. Our objective is simple. We start with elemental carbon and hydrogen and allow the system to reach thermodynamic equilibrium. Instead of defining specific reactions, we will use a Gibbs reactor which minimizes the Gibbs free energy of the system and automatically predicts the most stable products. This approach is particularly useful when multiple reactions are possible and the equilibrium products are not known beforehand. The first step is selecting all potential hydrocarbon species that may form during the equilibrium calculations. So along with the carbon and hydrogen, we will include methane, ethane, ethene, acetylene, propane, cyclopropane, propylene, and butane, isobutane, 1-butene, cis-2-butene, trans-2-butene, isobutylene. Including multiple species gives the Gibbs reactor the freedom to determine the most thermodynamically favorable distribution of products. A common mistake is limiting the component list too much, which can artificially constrain the equilibrium solution. Before we continue, pause for a second and leave your prediction in the comments. Which hydrocarbon do you think will dominate the final product stream? Next, we will select the thermodynamic model. For this system, we will use Peng-Robinson equation of state as the property package. It is widely used for hydrocarbon systems because it provides reliable predictions of vapor-liquid equilibrium and thermodynamic properties. For the reactor model, we will choose the Gibbs reactor. Unlike conversion, equilibrium, or kinetic reactors, the Gibbs reactor does not require reaction stoichiometry. Instead, it determines the equilibrium composition by minimizing the total Gibbs free energy of the system while satisfying elemental balances. This makes it extremely useful or powerful for exploratory studies and thermodynamic analysis. Here's where things get interesting. Since we haven't specified any reactions, the software will essentially decide for itself which hydrocarbons are most stable under the given conditions. Let's define the feed conditions that the feed is at 25 degrees centigrade temperature. The pressure of the feed is 2 bar. The molar flow rate of hydrogen is 100 kmol per hour, while that for carbon is also 100 kmol per hour. With, e with equal molar amounts of carbon and hydrogen entering the reactor, we will now allow the system to reach equilibrium. So now let's move to Aspen HYSYS and simulate the entire process. So first thing is to add the components. And what are those components? Carbon, hydrogen, CH4, which is, or we can say methane, then ethane, then ethene or ethylene, then acetylene. Then we will add the next component as propane, and it has been added. Then cyclopropane, which is C3H6 is added. Then propylene is added here, or is propene. Then butane, and that is N-butane. Then isobutane is here, as you can see. So we will simply add it. Then 1-butene is added. Then cis-2-butene is not detectable, so we will C4H8 and we will search with the formula name. So you can see cis-2-butene is added, trans-2-butene is added, and lastly, we will add isobutene or butylene. So we have added all our components in this list. Then we will go to the fluid package in add, and we will select Peng-Robinson property package. Then we will go to the simulation environment, and in reactor, this is the Gibbs reactor that we will select here. We will click on it, and we will do the connections of hydrogen and carbon. There are two products, vapor product and liquid product. Now we will define the feed. So that is at 25 degrees centigrade, 200 kPa or 2 bar, 100 kmol per hour. And since it's hydrogen, so its molar composition for hydrogen will be 1, while rest will be 0. And this stream, hydrogen stream, has been specified. Similarly, we will specify the carbon stream, 25 degrees centigrade, 2 bar, 100 kmol per hour. Double click on this flow rate to go to the composition, and we will select for carbon as 1. And once we select it, now you can see that the system has been converged. You can see that there is no liquid product in the system. Liquid is just for the connection in Aspen HYSYS, while there is a vapor product. And you can see that propene is produced, small quantity of ethylene is produced. You can see 1-butene, cis-2-butene, trans-2-butene, and isobutene. These are the main products that have been produced in the system. Obviously, in reactions, we had selected the reactor type as Gibbs reaction only. We can specify equilibrium reactions if we knew the reactions, or it could also behave like a separator as well. And if we go to this vapor product stream, and we will click on this composition and go to the basis and change it to mole flows, we can see that about 0.0045 moles for ethylene are generated, 0.4426 for propene, 0.0001 for acetylene, 0.6673 for 1-butene, for cis-2-butene it is 2.34, for trans-2-butene 4.78, and for isobutene it is 16.8679 kmol per hour, which is the molar flow rate that are produced in the system, and carbon and hydrogen are completely utilized in the system. So the key takeaway from the simulation is that equilibrium does not necessarily produce the hydrocarbon we may expect initially. Instead, the system selects the combination of products that minimizes the Gibbs free energy under the specified conditions. This is exactly why Gibbs reactors are so valuable during conceptual process design and feasibility studies. They allow engineers to evaluate potential product distributions before developing detailed reaction mechanisms. If you found this tutorial useful, please like the video and subscribe to the channel. Also, let me know in the comments what other Aspen HYSYS simulations you would like to see next. Thank you for watching, and I will see you in the next video.